If you look online about compilers and interpreters, you will hear a quite simple view on them, and here what I will want to try to achieve or explain is to get into a deeper view and some nuances and talks which I kind of heard people misuse it, even seasoned programmers. So let's get firstly what's about myself and so on. So I'm a software engineer, you can Google me, but the most important part about the topic is that I almost published and I worked in a system that it was, at least at the time, around 10 years ago, close to state of the art ahead of time compiler, which will take .NET bytecode and it would translate it in a high performing C++ code. And the talk is more or less about trade-offs, and I will use first of all two historical examples which will make we'll try at least to explain that the talk is not so simple, and I'll talk how interpreters are and so on. So first of all, if you Google or you go on YouTube, you will see typically a compile code. It is the code which gives you an exe and or a binary on Windows, on Linux, on macOS, and that's it. So people think that if you write the code and all the instructions are finally like in an exe, is compiled, and if not, is not. And to be fair, it's a simplistic, good enough view, but it's not quite correct. First of all, not exes are the same. So for example, if you use .NET, the exe just starts a virtual machine, let's say an interpreter for that matter, and it could be an interpreter depending on your machine, and the rest of the executable, it keeps the instructions which have to be interpreted. So there is no machine specific code. So let's take that distinction, and let's take the compile code is the one which gives you the assembler machine specific code for the user's machine. This abstraction also doesn't fully work because if you get a exe and you put it in an MS-DOS machine or a very old version of Windows or macOS, it will not run. So it's clear that the operating system would also work in a way like an interpreter, and sometimes even if you have a target operating system which you may know that the operating system will do emulation to run your code. So if you make an EMD64 app, it may run on an ARM CPU because the operating system, be it Windows or macOS, could give you emulation. And also, even if you have the same CPU instructions, there are platform emulators like Wine on Linux that can run a DLL like a Linux binary, or there is Windows subsystem for Linux. So there is a big chunk of discussion, but in general, if you take the code and you build it more or less to CPU instructions, people would agree it's compiled, and if not, it's not. So with this taken away, most people think about the interpreters that they are very slow, and probably they are, and I'm using probably as we will discuss a bit more, but sometimes even it is slow. It may be by far not the slowest part, so you may not even care. Erlang, for example, it is used as a language to manipulate many processes, to coordinate, synchronize, to run a process. And all this logic is done in an interpreter, but the Erlang code is never the bottleneck. If you have a game and you run it in Python, even though Python is 50 times slower, maybe 100 times slower, if your game is simple enough, I will use Candy Crush, but this is not uh, an attack of how simple is Candy Crush, because there is a lot of work in a game like that. But if you make a Candy Crush like game, Python will never be the bottleneck, or it will be very little if you know how to code it. So let's go further. And most people, when they met the discussion about interpreters, probably it was, if you, at least your parents, if they did coding or they got a computer, it was very likely a microcomputer, and it was running BASIC. And BASIC was with an interpreter in it. So the first thing you could see in such like machine, it will be literally the machine starting an interpreter. And there is no one way to show it, but I will use an emulator. So to look like this. So the first thing you will see here, it will be a basic interpreter. This is an emulator, and here you could write probably print 2 plus 2, and it shows to you the 4. You can give a line, print, this is basic, basically 2 plus 3, and then you put 20, go to 10, and run, I think, and it will show to you 5. And this was the basic in a nutshell. I'll close it, but this is how users would see computers, and all this code was interpreted. So one part which many people may not know, it was that even BASIC was done, at least implemented and created at least 20 years before you will have this microcomputer. This code was compiled. So why did they go from let's say faster machine or to a microcomputer to go interpret it when you will want performance, for example? And the first part which we should think of, it was that the big computer in the university was a mainframe, and not everyone can afford to buy a mainframe, especially as microcomputers were very cheap computers. So people would want to have a simpler computer. So a compiler, especially an advanced one, would be out of reach, and most people will not pay double the cost. So the 2 plus 3 is calculated 100 times faster, even if it would be that fast, because you'll still not be limited by this aspect. So let's go further away. So for example, for the Commodore 64, which I showed to you in an emulator, you will see that there are 38 kilobytes accessible as free memory, but in reality, and people, if you Google it, you will see that the interpreter, in fact, it occupies 4K, and you had some banks of memory if you knew where to use it, and depending of what your game was using. So if you use, for example, the drawing routines, but you'll not use character sets, you could very easily rely on to get more memory, up to kind of 60 kilobytes of memory. The other part, which was a big advantage on Commodore 64 or on Sinclair Spectrum, which I was used to have, at least a clone of it, it is that the basic language is smaller than the final compiled code, and the savings, they depend between the platform and the specific implementation of the bytecode. But the smallest savings I could see, it was a 2.5x factor from at least .NET to C++. It's not the same as BASIC, but I've seen presentation of 6x, which is quite reasonable in my understanding. Also, if you compile it for speed, the size will increase. And the runtime performance, it was around 10 times slower, but this 10 times slower, it was only in the basic code. So the printing code, it was written basically in assembly, or to draw a line, again it was written in assembly. You had the same performance like of C, excluding the start preamble to set up the drawing method, the parameters. And similarly, it was the same for circles and playing a sound for that method. So the performance was not as fast, and as I was saying before, it was not that slow, because you could see in that emulator that when you click enter, it answered to you kind of right away. It was not a slowdown, but the user, and it may surprise some. So, but if you didn't do your special computations, in fact the compiler could slow down, because you'll have to compile, validate command by command, try to make some optimizations, try to put an intermediary structure, and so on. And this is complicated coding, and an interpreter realistically was much simpler. So it will give you right away the answer. So imagine you'll write a print 2 plus 3, you press enter, you wait 3 seconds, then it shows to you a 5. Even though the code will be compiled, it will not be faster than you write print 2 plus 3 and gives you right away 5. Even though if you put it in a loop, it will be after that 10 times faster. So we can go further away with other example. So Java, it is also known, and many people say today it's interpreted, which we will talk a bit, but Java was a bytecode interpreter, and this is an important distinction. And some basic language interpreters were the same. So when you write in basic print, at least in a simpler spectrum, and in Java for that matter, that print is encoded as basically 1 byte, and the syntax is validated, is correct before the code is executed. And at least Java, when it was launched, even it has a bytecode interpreted code base, many, let's say, critical parts that were more or less heavy in memory usage or computation, they were written in C and they were invoked from Java. So the displaying of Windows was using AWT, which was basically a small set of classes on top of Windows or X Windows. So to create a window, it will be as fast as Visual Basic was on the time, another interpreted language, but it felt fast enough. And the same it was about the drawing routines and so on. They were also written in C++ or C. And the garbage collection was written in similar way in C, and native access was written in C. And later, in end of 90s, Java being very popular, there were live compilers which are named just in time, and Hotspot won the way kind of how Java is implemented today. And let's talk about Hotspot a bit. So Hotspot is technically an interpreter, and some people use this term, but they use it kind of saying because it's slow, but in fact it's not that slow. So initially, when the Java bytecode starts to be interpreted, which are defined operations, it reaches a loop count. It goes through the instruction, and if it says, look, I evaluated this instruction for, let's say, 1000 times, it says to the Java runtime, please compile it with C1. C1 meaning it's a fast compiler, and this C1 would make it run faster, this code. But what's the most interesting part is that it will add also counters. So it will add counters to say which branches of the loop should be more aggressively compiled. So when the C2, the advanced compiler, works, it will not only optimize the code, but it will optimize based on the branches of the code which it notices you are using your code. So it is a what is named a speculative compiler, and it is so good that in enough many benchmarks it can beat C++, which is known C++ as being very fast language, or in some other benchmarks it gives like 99% of the C++ implementations or Rust implementations. And this approach is the Java 8 till today. So it's from 2015, if I remember, so a 7 years old understanding. So when you write Java code in particular, even though it's interpreted, to use this term, you don't complain about performance, or you should complain of memory usage. But okay, so one part which will go a bit on the meat of the talk is that, let's say you have your own language, or you want to look to the language from the performance particularly standpoint, but you want to check what type of compilers or interpreters are around. And the first thing which when a language is made, after you evaluate your language, typically you create what is named an AST. This is a tree kind of structure, like your directories in Explorer, and this AST structure can be evaluated going and visiting all the leaves. I think the Lua is doing this structure. JavaScript is doing this structure. It's written in C++ JavaScript, and it could be very slow compared with a bytecode interpreter. So we talk really kind of even 10 times slower or 4 times slower than having a bytecode interpreter. And the change is that the bytecode interpreter basically it visits the tree and it defines operations in an integer form, because computers love numbers, but they don't love to go through memory left and right. So most of interpreters today, when you say it's interpreted, in fact it's a bytecode interpreter, which means that the compilation is already done. And this is true also for JavaScript, Java, Ruby, Python, and I think many other interpreters. And if you write your own interpreter, please look to make a bytecode interpreter, and this would probably address most of performance issues from a person using your language, excluding this not very critical code. And after the bytecode interpreters are defined, people try to get performance typically just in time. And just in time means like when you call a method, you have this bytecode, you make a compiled code of it. You make a really live code and you set the function pointer to execute that function. And if you use a thing, let's say you use .NET, and many high performance runtimes would use typically the unit based is the method, so your function. So you call main, all the bytecode or operations are compiled and it creates a method, and all the sub methods which you would call, they will have something which is named a trampoline or a trap. And when you call that method, the child method, it will look, is it compiled already? If it's so, the pointer changed to that compile form. If not, it will compile like the new method, and then it will set it as a pointer to that function. And The method-based JITs, they have a big disadvantage, typically, that it takes too long to do advanced or heavy optimizations. Hotspot, it's smart enough to know what to optimize and when the counter is high. But if you have a count of 1 and you do a heavy optimization, the application will run slow, obviously. So a side solution, and I've seen just one project doing it, and it was, I think, Open Desktop, I'll have to look for the name, is that sometimes you can mix just in time with what is named just too late. So like you'll use a just in time with simple optimizations, but because you know that this method was used and it looks useful, you will compile it with heavy optimizations in background. So you'll launch a compiler process in the background, and it will take the same method of before, but it will do aggressive optimizations. And the next time when you start your program, it will use from this heavier compiled methods instead of using the simpler just-in-time. A very interesting talk is both templated compilers. And a templated compiler, it says you define your code in, for example, in your interpreter, and you look what your compiler code will generate in assembler, and you take that code, you'll assemble it with a binary, and you paste it inside of your bytecode, and it looks like an interpreter. You just join together all the operations of the interpreter, but it gives you a very good baseline performance. It's simpler to be done than a full compiler, and you choose which optimization you should do. And it's used also, for example, for a C1 kind of compiler. If you implement a future architecture like Hotspot, a templated compiler is a good starting point. But the most interesting mix of optimizations, I think, are the tracing JITs. And the tracing JIT, it talks about to have a trace, and a trace means in compiler theory that you have a code without jumps, without if, and without goto. And typically when you have your mathematical code, it will look like this. So all this mathematical code, you can compile it, and it gives very big speedups, in fact, obviously on mathematical code, but it will not give speedups if your code is very if else. But this is fine, because sometimes it's worth to have your code, only the hot mathematical code, to be accelerated. And it was very successful, for example, in Android. Android had few years, I think 4 or 5, at least, this initially interpreted, then this tracing JIT, and it has very many advantages. So first of all, it's much simpler. It is very small. You'll optimize just a subset of your operations, but it's also very good that you can fall back. So you will see, for example, that there is a division, and you are afraid that that division can give you divide by 0. You can check before generating the code, is it that variable 0, and if it's a 0, you handle it properly in your interpreter code. You will not handle it in compiled code. Or you can not interpret at all the code, or you don't compile at all the code, because it has a very unexpected instruction which you don't want to handle it. And kind of that's it about JIT. I will make probably in the future a talk only about tracing JITs and tracelets. But let's go also about the ahead of time compilers. So most people, when they talk compilers, they talk what we will name ahead of time, that all the operations are defined at compile time. And as I said, even Java technically is an ahead of time compiler, because it validates the syntax and generates bytecode. But on a more important note is that, for example, Java, you can't compile it everything ahead of time. there are, at least by Java specification, cases when you'll need to handle when the code is generated, for example, out of configuration, or you have a class, I forgot how it's named, class loaders, I think, that you can get classes at runtime, and there are solutions that you'll do ahead of time compilation, which is great, but you fall back to a JIT or an interpreter. And one part which is surprising for many is that today many people think that our code is every person compiles the code, but you'll be surprised how much code is just in timed. But most of the times it's around pixel shaders and vertex shaders, and NVIDIA was the first to create a cached version. So when you say to your graphic card compile the shader, the driver will create a local cache on disk, so next time it will read it from disk instead of compiling. So it would worth to do advanced optimizations. It works, like as I said earlier, with the just too late, but this time it will be an aggressive optimizer, and it will always save down the output. And there are variations on this in the Java world, in special OpenG9. You should look if you are curious, and Azul's Red Now on the Java runtime side. So kind of that's it on the types of runtimes. But if you create your own language, what would you use, or what should you use? And I would say by default you should go kind of right away to an interpreter, or I will talk something a bit later, but the advantages are huge. So for example, it's much simpler to create an interpreter, and especially try if it's a bytecode interpreter, it is also quite fast. And if you need some performance, you can create a tracing JIT, and the tracing JIT, it will be only for where the customers would pay for it or something like that. It takes less effort to do than a full JIT. It is also, because it's compact as a bytecode, typically it will fit in a very small machines, like 64 kilobytes of RAM kind of machines, even though it will be a bit slower. And if you have some code which is very hot, you have to draw a lot, implement only that method in C++ or whatever language is fast, Rust. And the advantages, they are amazing. So you can add batteries, so you can add routines that are useful even after the fact. So you can set up some bytecodes that you don't use just for debuggability, or to add a printing routine. And also it's very good when you scale it up to can scale it down. You can drop functionality even from VM. Your interpreter or virtual machine may not have compiled into it any networking, any disk access. It can read from console, write from console, basically to work on a diskless system. And it will be very hard to hack this part. It's easier to debug, obviously, an interpreter, because you don't read the assembly code. And let's say your product is so successful that you really want to eventually to be as fast as C++, you can do it after the fact. And to have this kind of interpreters which will go compile with hot code. And this is what happened with JavaScript. So JavaScript today, it works very much like hotspot, but it was after companies get millions of users and millions of funds to work on it. There are advantages though if you work on a compiler, that you compile the code, and the biggest one which many people state is about very fast startup. I would say if you don't include the compilation time, so if you are a developer, you not have very fast startup, you'll have to compile your code, obviously. And but let's say you care only about the users. And also, if you care about the users, at least today there is a lot of theory, and compilers can do amazingly big optimizations, especially if you use link time optimizations and or combine with profile guided optimizations. So thinking about that, you may really want to output, for example, C++. And why C++ is because there are IDEs on every platform which can help you debug. So the hard problems which interpreters, they sort them well, they are sorted out by big corporations, let's say Apple's, or on Linux will be probably Intel, or Microsoft on Windows. They have very good ideas to debug the code, or to sort out some security issues, or to attach a debugger or something like that. So if you output with your language, even Java as Java code, not Java bytecode, probably you'll have all the advantages of a low-level platform, but you'll also get automatically the performance, which is very nice. So kind of it, that's all the talk about. So if you like it, please subscribe, join, share, and I will make more clips, probably in particular techniques. I will want to do only one about tracing JITs, because it's quite little known, and I will add more, probably about ahead of time compiler optimizations, and why are they so interesting. Thank you, and bye bye.